So, good evening, everyone. I hope you had a nice break. Today's session is focused into revision for your PPE, for your mock exams. Just checking if the sound is good. Let me see. Yeah, perfect. I can hear myself, so the sound is going very well. Wonderful. I don't have the visualizer, so I will use the iPad, and it's a bit difficult to write on the iPad, so sorry for the handwriting. Asking for apologies in advance, and we will jump into some exam questions I have selected for this session. If the exam questions you would like me to solve are different, or you would like me to do any other sort of topic, please don't forget that you can write me anytime through any of the social media about what topic would you like to do about. Anyway, let's go into here. Okay, so now normally I will use the visualizer, which is much easier because I can write on a paper, but today we're gonna use Paint. Sorry. Once we are back in school, I will bring back my visualizer. Anyway, can you read the questions properly? Because Paint is a bit complicated in the sense of it looks or very far or very close, but there is no like middle ground. Let me double check. Okay, seems that it's a bit far. Let me see if I can. Okay, that's gonna make it. Oh, let me see if I can manually make it smaller. No. Anyway, I will read the question and then I will zoom out. Question 1 says different radioactive isotopes have different values of half-life. What does it mean by the half-life of a radioactive isotope? Okay, so the first question is asking us what is the definition of a half-life. If you remember, I already did a video about this, a video that pretended to be funny. I don't know if it was funny, but it was about Twilight. Half-life, let me see if I can write in here. Half-life is the time needed to reduce the amount of radioactive isotopes to the half. What is the meaning of this? We have radioactive isotopes, all right? And because they are radioactive, okay, now it's not giving me, all right. Let me make it like bold. I cannot make it bold now. Anyway, that's the definition of half-life. The time needed. Half-life is always time. It can be seconds, it can be days, weeks, years. It's always measured in time. And the radioactive isotopes, they are not stable. They are unstable. So they are radioactive because they are unstable, but once they emit radioactivity, once they emit that energy, they are not unstable anymore. So they are turning into more stable. So once they decay, we consider that they are not radioactive anymore. So the time that it takes to reduce the amount of those isotopes to the half is half-life. So imagine we have, I don't know, we have a sample, we have a box with 50 radioactive isotopes. So the amount of time that it takes from those 50 to turn into only 25, so 25 isotopes that they are still radioactive and 25 that they are not radioactive anymore, how long does it take for that process? That is what we call half-life. And we measure half-life because radioactive decay is a random process. We don't know when it is going to happen. Radioactive decay, which is the process of one radioactive isotope to emit radiation, can happen now, 1 day, 2 days, 3 days, 4 days, 1 million days, 1 million years. It's a process that it is random and it cannot be accelerated, or let's say delay. We cannot control it. That's why instead of finding out exactly when the radioactive decay is going to happen, we use half-life, which is like an estimation. It's the best that we can do, let's say. Okay, I hope that the definition now is clear. Also very important is the graph of half-life. Half-life graph, they always have this curve shape. Doesn't matter what radioactive isotope we are talking about, they always have the same shape. It's never a straight line, it's always a curve. And it's always a curve that is what we call in maths asymptotic. What is the meaning of asymptotic? That it never reaches to zero. And if you think about it, it makes lots of sense. Because if you have, for example, in this case, we have 80. How much is the half of 80? 40. Half of 40, 20. 20, the half is 10. The half is 5. The half is 2.5. The half is 1.75. And we could continue like that and we would never reach zero. Is what we call asymptotic. It's a graph that never touches zero. Alright, so if they give you this graph and they ask you calculate the half-life, how do we do it? It's much easier than you think. First of all, you need to look at how much is the original, let me see if I can use how much is the original amount of radioactive isotopes that we have. In this case, the original amount of radioactive isotopes is 80. So then you need to think about, if 80 is the initial amount of radioactive isotopes, how much is the half of 80? Well, you see, it's 40. Alright, and 40 is here. So based on the graph, how long does it take to go from 80 to 40? Sorry if it's not very straight line, but you know I'm using the iPad. It's like not very easy to do a straight line. So now we come in here, we draw straight. If you have a ruler, it's better. And now you go there to our graph. This is a graph that is for a particular radioactive isotopes. Different radioactive isotopes, they will decay faster or slower, but this one is the one that they gave to us. So then we go scroll down and we see how long does it take to reach to that point. Again, if you have a straight line, is better. I think I can do a straight line. Let's say there is the point, so straight line will be something like that. In days, it will be approximately like 59 days, approx between 50 to 60. They always give you like a range, so they will give you like 50 or 60. If you put any of those, that they will give you probably the answer. I would say 59 days, because it seems that from my perspective, it doesn't reach to 60. But that's it. This is half-life. This is how we find out half-life using the graph. As I mentioned, it's very easy, but I will repeat very quickly for those who just joined. Check how much is the original amount of radioactive isotopes, how much is the half of that original amount, and based on the graph, how long does it take to reach to that point. Easy peasy. Next question. Show clearly on figure 1 how you obtain your answer. We have done it, okay? We have shown in the graph, just with 2 straight lines, how we find out half-life. It's pretty easy, pretty straightforward. The table below shows data from some radioactive isotopes that are used in schools. For example, americium-241 is the one that we find in the smoke detectors. And americium-241 emits alpha and gamma radiation. Remember that there are 3 types of radioactive radiation: alpha particles, beta particles, and gamma radiation. Super important. Gamma is not a particle, gamma is radiation. So it's alpha and beta particles, and then gamma radiation. And then you have the half-life in years, which is how long does it take to reduce the amount of radioactive isotopes to the half. And you see that some elements, they decay faster than others. For example, americium-241 is 460 years. Meanwhile, cobalt-60 is 5 years. But thorium-232 is more than a million years. You see? Not all the radioactive isotopes, they emit radiation at the same rate. Some of them they emit faster, some of them they emit slower. And also, they emit different particles. State which radioactive isotope in the table above emits only radiation that is not deflected by a magnetic field. Give a reason of your choice. Okay, let's stop in here 1 second and let's draw a magnet. If you remember, a magnet, let's say a bar magnet, like this. This is a bar, and this is our magnet. All the magnets, they have two poles, north, south. And for those who are already at the end of the topic, you remember that a magnet has a magnetic field that looks like this. It has like lines, magnetic lines, that they look like this. It looks very ugly. But anyway, the north, it will always say in terms of charges is the positive. And south, in terms of charges, is what we call the negative. And if you remember, there are 3 subatomic particles. One subatomic particle, which is the proton, that has positive charge, meaning that it is repelled by the north, but is attracted to the south. Then we have the electron that has negative charge, meaning that it is attracted by the north, but it is repelled by the south. And the last one is the neutron. The neutron doesn't have any charge, neither positive, neither negative. So it doesn't feel any interaction with a magnet. Same thing we have, because you might be thinking, what is the relationship between what you are telling me and the radioactive decay? Very simple. Or for me, it's simple. You can tell me if it's not simple. And you're not telling me anything in the chat, so I imagine that you also think it is simple. We have alpha, which the symbol is like that fish, but it's the Greek letter alpha. Alpha particles, they have charge. Their charge is +2. Beta, which the symbol is the Greek letter B, beta particles, they also have charge and is -1. And gamma is not a particle, it is radiation. And what is radiation? Radiation is just energy. Energy like light energy, sound energy, microwaves, radio waves, ultraviolet, and it doesn't have any charge. Any charge. What is the meaning of that? So alpha, for example, if I put a magnet north-south, alpha particle will move away from the north and will go to the south. It will feel attracted by the south. Beta, north and south, it will be repelled by the south and go to the north. And gamma will just pass straight. Why? Because they will not have any interaction. Because being attracted or repelled by a magnet depends on your charge. Since gamma doesn't have any charge, it would just pass in a straight line. In a magnet that looks like this, in a magnet that looks like a, imagine it looks like a tunnel, or like 2 bars, 1 bar is north and 1 bar that is south, the alpha particle will deviate down, actually will deviate heavily down because it's also very heavy particle, so it will enter in the magnetic field and deviate it down to the south. The beta minus will deviate slightly to the north. It will deviate less because it's very, very tiny. And the gamma radiation is a wave, will just pass straight. No deviation because it doesn't have any charge. That is the reason. All right, let's go back to the questions. I think I have explained it very well. I mean, not very well, like I have explained in detail why this is the reason. Figure 2 shows a radioactive isotope being used to monitor the thickness of paper during production. And we have a radioactive isotope and a detector. And the purpose of this detector and radioactive isotope is that if the paper gets very thick, the radioactive isotope will not be able to reach to the detector, or if the paper gets very slim, lots of radioactivity will reach to the detector. So the detector will tell us if there is any change in the thickness of the paper. And it is a real use of radioactivity. It is a real use of radioactivity. State which radioactive isotopes in the table should be used to monitor the thickness of the paper. Explain your choice. There is only one possibility, which is beta decay. Only one. Why? It cannot be alpha because alpha will always be stopped. Alpha particles, they have very low penetration power. So with just a very little piece of paper, you stop all the alpha particles. So it doesn't matter how thick is the paper will always stop the alpha particles. And gamma is the opposite. Gamma has very high penetration power. Think that gamma is able to pass through concrete, is able to pass through iron, is able to pass through lead. So the paper will never be able to stop. So gamma will not be able to monitor the thickness of the paper. That's why beta is the only possible answer. Am I going very quick? Nobody's telling me anything. Am I going very quick? Anyone in the chat would like to tell me if I'm going very quick or not? Is the connection good? Is everything good? Okay, I want to believe that everything is fine. Fantastic. Okay, so let's continue. State which source in the table will need to be replaced most often. So again, back to the table. Which one we will need to replace more often? Obviously, cobalt-60. Why? Because it has lower half-life. If you look at, after 5 years, the half of cobalt-60 is not radioactive anymore. After 10 years, 75% of the cobalt-60 is not radioactive anymore. And so on, and so on, and so on. Meanwhile, all the other elements, it takes much longer to reduce the amount of radioactive isotopes. So the answer is cobalt-60. Cobalt-60 because it has a shorter half-life. There you go. Easy peasy, lemon squeezy. Following question, next question. When the radioactive isotopes are not in use, they are stored in lead-lined wooden boxes. The boxes reduce the level of radiation that reaches the surroundings, and they are giving us an image of the box. In the school, we have something similar to this. State one source from the table which emits radiation that could penetrate the box. Explain your answer. We need to go back to the box. They are saying that the box is made of, and I will highlight it, is made of lead wooden box. So a radioactive decay that is able to pass through lead wooden box can only be gamma. Only gamma. Why is that? Alpha particles, as I mentioned earlier, can be stopped with just paper. Just paper sheet, stop alpha radiation. And beta can be stopped with aluminum foil, something like that. Just aluminum foil. I don't have any aluminum foil around me, but aluminum foil can stop beta particles. Therefore, if we have a wooden lead-lined wooden box, only gamma radiation can pass through it. So, which are the elements, which are the radioactive isotopes that they can pass through? Americium, cobalt, radium, and that's all. So those three: americium, cobalt, and radium. Americium, the symbol is Am. cobalt is CO, and radium. Why? Because these three, they are able to emit gamma radiation. And gamma radiation has penetration power to pass through the box. All the others, they don't have enough penetration power. Okay? Guys, we are almost at the end. Thank you very much for holding. Here we have question 2. The diagram represents an atom of beryllium. Okay? Fantastic. And they give us the diagram. Also remember that this diagram is not to scale. The electron is much smaller. It's 10,000 times smaller. So this diagram is not to scale, okay? And they label it with J, K, L. Complete the following statements by writing one of the letters J, K, or L in the box. Each letter should be used only once. The particle with a positive charge. If you remember, the particle with a positive charge is the proton. And now you might be thinking, well, what if I don't remember? What if I don't remember how many protons are there in beryllium? Well, you need to use your periodic table, and they're going to give you one periodic table in the exam. You need to look at beryllium, and you see that beryllium, I believe, beryllium has atomic number 4, but let me double check. I think beryllium has atomic number 4. Just 1 second. Beryllium. Yes, 4 and 9. So 4 and 9. What is the meaning of that? That 4, which is the atomic number, is telling us the amount of protons. So if you look at the graph, the diagram again, which one is the one that has 4? 1, 2, 3, 4. You see? If you look at the atom and the letter L, we have 4 of those in the nucleus. Remember that the proton can be found in the nucleus. So in here, in this diagram, we have 4 protons. And we have 1, 2, 3, 4, 5. I will not say 6, 7. 5 neutrons. And we have also 1, 2, 3, 4 electrons. Okay? So now we can answer all the questions basically. So this is L. The particle with the smallest mass is J, I think. Yes, because it's the electron. And the particle with no charge is K. Easy peasy. Look at the diagram again. L is the number of protons, because we have 4, and beryllium has atomic number 4. Remember that the atomic number refers to the number of protons, and is unique for each element. 1, 2, 3, 4. 5 is the number of neutrons. They don't have charge. That's why they're called neutrons, because they are neutral. And then we have J, which are the electrons, and they are the smallest one. Easy. Give the reason why all atoms have total charge of 0. There are 2 charges, positives and negatives. Positives given by the proton, negatives given by the electron. Normally, if the atom is neutral, is because the amount of protons is equal to the amount of electrons. That's what we're going to write. Charge is 0 because number of protons is equal to the number of electrons. Okay? I know we are mixing here with chemistry, but as I say to my students all the time, whenever you are revising, don't revise like knowledge is like a box and it's not connected with anything else. All the knowledge, everything you learn is connected. Let's finish quick. Okay. Complete the following sentences. There are several isotopes of beryllium. Atoms of different beryllium isotopes will have different number of neutrons. What changes in an isotope is the mass number, not the atomic mass. Sorry, not the atomic number. So in beryllium, for example, 4 cannot change. You will always have beryllium 4 because 4 is the number of protons, and that cannot change. If you change that, you are changing the element. And 9 is the number of protons plus neutrons, and that one can change. You can change that by adding or removing neutrons. That can change. And there are some isotopes that they are more stable, and there are some isotopes that they are less stable, and they are radioactive. The topic is very interesting, but I don't want to overextend the session. I know you are tired because it's Sunday, so let's finish. What happens to the structure of an atom to change it into an ion? So an ion is an element that has different charge. And how they have different charge? By removing or adding electrons. That's how we make an ion. If you add electrons, if you, for example, you have, I would choose, for example, one very common. If you have oxygen, and oxygen gains 2 electrons plus 2 electrons, oxygen now turns in oxygen 2 minus. Why negative? Because the electrons, they have negative charge. On the contrary, if you have sodium and you remove 1 electron, that turns into sodium plus 1. Why? Because when you remove electrons, the atom gains positive energy. Think about the scale, and I recommend you to see a website called PHET, something that's called Build an Atom, and that will show you a scale where you will see how changing the amount of electrons and changing the amount of protons, don't change the amount of protons, sorry, changing the amount of electrons will modify the charge of the atom. An ion is always changing electrons. Adding electrons, make it more negative. Removing electrons, make it more positive. Is there, hello, Simple Circle. Is there anything that you would like me to revise again? Sorry if it was a bit laggy. I changed the internet provider at home, and it's still, adapting. I hope in the following streams it gets better. But apart from that, was everything clear? Was there anything that was very fast? Anything that you would like me to re-explain again? What do you think? This video is going to be recorded and it's going to be shared in YouTube. So if you want to watch it again or the exam questions, feel free to do it. And if you have any further question or something that you would like me to re-explain again, please feel free to contact me in any of the social media, Mr. Romero Science, and I will be more than happy to redo it again in the next live stream, which I hope is going to be soon. Let's get a positive routine for this new year, and let's see if I can help you as much as possible with all your revision and all your homework. That's everything from me, guys. Enjoy the rest of your Sunday. See you back tomorrow in school. Stay tuned for more videos. Ciao, ciao.